Yeah.
Great. And can you see my screen?
Yeah.
Good. Okay. Well, great. I'll launch right in, and if there's any issues, somebody please yell. But yeah, thanks for the invitation. Very happy to speak with this group. I think it's a great place to be right now. And start by acknowledging my group members, some current and former group members who've done a lot of interesting work, as well as really good collaborators. And I think this audience should be very receptive, right? We're changing how we do research, and we're changing how we'll do research in the future significantly. It really is a turning point, and I'll talk about that as we go along. But I think one of the things that's really captured that for me is this challenge that's issued by Professor Hiroaki Kitano, who's a fellow at Sony, this Nobel Turing Challenge, which is, can we build machines that can win a Nobel Prize by 2050? And so the way Kitano sees it is these two axes of autonomy and intelligence, where they are sort of independent. You can have autonomy without intelligence and vice versa. And the other part I'll point you to in the lower left of the plot there, that his quote, that scientific discoveries at the pre-industrial revolution level, right? And so that's telling. We think of ourselves as high tech, but honestly, when we look at our workflows, they're not as high tech as we think they are, right? They're very much human oriented. There's lots of glassware and human pipetting, all this kind of stuff involved. I work on carbon nanotubes. In the interest of time, I'm going to go through a lot of this quickly, but really the challenge is that nanotubes should be available at megaton quantities, but for a lack of understanding, we should be able to have carbon nanotubes as a commodity polymer, like polyethylene. And the save the world proposition for carbon nanotubes is that if we can take methane, which we currently burn and emit CO2 at hundreds of millions of tons per year, causing global warming and really bringing our Earth to a catastrophe. If we pyrolyze it and extract the hydrogen, send it to the hydrogen economy, and use that carbon instead of as CO2, we sequester it in the form of carbon nanotubes. So not only have we avoided CO2 emissions and saved the planet in that sense, now we have a material that we can use, and carbon nanotubes is a wonderful material that can replace copper and aluminum for conductors and polyethylene for lots of plastic applications and steel for structural materials. So there's a huge impact to the materials market if we can do this successfully, but the asterisk being that we don't know how to make carbon nanotubes at scale. So we built Ares, autonomous research system, to as a robotic system, an autonomous robotic system that essentially taught itself how to grow carbon nanotubes at controlled rates. And I won't go through the details. I've been through it plenty of times before, and the paper is down at the bottom. But we were the first ones to do this for materials, and so that's been very exciting. And since then, there have been a lot of others who have launched into this, which again is very compelling and a new way of doing things. But just to think abstractly about the research process, the core part is this loop, right? Where you plan an experiment, you execute the experiment, you see what happened, and then you use that new information to improve your planning for the next experiment, and then you iterate. And I guess some of the things to point out is, right, there are different things you can do. You can predict that something will work. You can strategically explore understood areas, places that are not well understood, or you can exploit. You can try and maximize. You think you're close, but do maybe some kind of a gradient approach to marginally improve your results. And similarly, experiments can really be a normal hardware experiment, but you could also do a simulation, right? You could do a natural language extraction. So that's the experiment part. Really, it's essentially generating new data to incorporate into your understanding. And so this analyze part is really about extracting that knowledge from the experiment to interpret, explain, reason, understand. And so you do that loop. And of course, the loop has an entry point and an exit point. So the human is over here defining the constraints, the objectives, providing prior knowledge, and then, the conclusion block. And so the important points here is that, the autonomy is where the system designs its own experiments. Automation is where you're able to do that without human intervention. Decision-making is key. That's a distinction from AI applied to characterization. It's the decision-making. And eventually we want to get to hypothesis generation and testing. So again, on the AI ML part, this generation block is where we're generating new information, and lots of folks are doing an AI to analyze data. So you're trying to understand what's out there, but it's the decision making, I think, that's new in this area, where you're having to make a decision towards an objective. So what do I want to do? I want to maximize a property, or I want to confirm a hypothesis. These kinds of things are sort of newer to the community. So another more recent example is with Chris Reyes at the University of Buffalo on nanotube synthesis. So his Holmes knowledge gradient decision policy really starts to incorporate some hypothesis. In this case, it was a hypothesis about the state of the catalyst and whether it was oxidized or reduced. And so the result was that we went from this kind of zoo of different nanotube diameters. So this is Raman spectroscopy, where the small diameter is to the right and the large diameter is to the left. And what we'd like to do is have selective growth, where we only have one of these peaks. And so after a number of iterations, we got a very significant improvement in our target peak. So a 5x improvement in selectivity for the correlative nanotube that we're looking for. Along with it, we got some better understanding of our hypothesis about catalyst oxidation and reduction. So we're at this technology trigger point, right? We're really starting to have a huge upturn in people doing autonomous experimentation, and it goes by many names. There's materials acceleration platforms, self-driving laboratories, but it's generally something where we use autonomy, artificial intelligence to do closed loop experimentation. And if you're looking for a review, we had this paper out last summer that came from a workshop in 2019, and it really maps out not just the state of the art, but the directions, the needs, the kinds of investments that we'd like to do. And again, this has, a snapshot, if you will, of some closed loop autonomous experimentation campaigns. So at Cornell University, Professor Carla Gomez is using reasoning. So Sarah is for scientific autonomous reasoning agent. And what's distinct about the Cornell approach led with the AI led by Professor Gomez is that they're using reasoning to constrain it. So it's not data-based, it's knowledge-based, and the knowledge is embedded, in this case, in the understanding of phase diagram behavior in materials. So things like constraints from Gibbs' law, for example. Keith Brown at Boston University really did some nice work on autonomous experimentation, where he used topological optimization to print a twisted barrel structure. He has this bank of 3D printers, and the robot would then load the structure, printed structure, into an instron. It would crush it and get out the energy absorption. And the thing for Chris was that he was compared it to essentially a Latin hypercube campaign. And so in a good comparison, he was able to demonstrate a 60x acceleration. So that's a great data point, a great metric that autonomous experimentation in this case led to a 60-fold acceleration over conventional design of experiments. So of course, Marty Burke at UIUC has his wonderful molecule maker, and we've been working with Marty to essentially make it closed loop. So we're calling it the molecule maker ARI system. And so David Simone has been building this in collaboration with Marty and Nick. And essentially, we took the molecule maker as designed by UIUC and put an NMR tool on it. And we're now able to do closed loop Suzuki coupling reaction where we make something, we send it through an NMR, we characterize it, and then we iterate and do iterative improvement. At first to improve yield, but eventually to design entirely new molecules. And so we do this with our Aries OS. I won't go into the details much, but we're able to set up a custom dashboard for Molecule Maker Aries. And so if you want to build your own research robot, we're trying to make it easier. So we took a 3D printer, and in about 6 months, we made it closed loop. Essentially, we print something out, take a picture of it, and then adjust all the different input parameters using a Bayesian technique in this case to better meet our goal, which was to fill the line start, this green line here. We have planning via online from Amazon Web Services, and then our Aries software. And this is an old slide, I apologize, but our Aries OS is out. And now we're trying to build an educational Aries, a low-cost printer that we hope to deliver for about $300 to really lower the barrier to entry so that anyone can build their own fully closed loop autonomous research robot and try out their ideas on autonomy or ideas on 3D printing. So here's a quick video of this Aries printing out a square and filling it, and then it's going to go over, this is the camera over here, it's going to take a quick picture and score it, right, and show where it didn't fill very well. And the black line here is that score, and it's trying to get to 1 by adjusting these 3 different parameters here. And so just a simple demonstration of how closed loop iterative experimentation works. So again, if you want to download Aries OS, it's at the GitHub there, and I can put it in the chat afterwards. But really the idea is for it to provide a software framework for everyone to build their own autonomous research robots and reduce the barrier. And so there's still programming to do. You still have to build the app to your particular robot instantiation, but a lot of the core framework for essentially building up sequencing and robotic handling and all of that is implicit in the Aries OS. Okay, so again, moving on, just to try and think of this as a revolution. You know, the Industrial Revolution is where we had machines, engines that could do the work of 100 humans or 1,000 humans. And so that transformed farming and manufacturing and changed the way we did work, right? And we went from, you know, craftsmen who would build things one at a time to factories who would do mass production. On the cognitive end, thinking about, you know, calculations in this case, when in the 40s and 50s, if you said computer, you were usually referring to a person. And so, for example, you know, there were rooms full of people, mostly women, who were using adding machines to calculate firing tables. And so then Melba Roy led this group of human computers and then onto the mainframe computer to do calculations for NASA. And now we don't even think of our cell phones as computers, but they are computers, and they really offload the cognitive work that we could take years and years to do or simply could not do, and fits in our pocket. So that's a real revolution. But the idea is that robots can perform both cognitive and manual labor. So again, you know, why aren't we doing that for research? And so you're seeing some great examples of that today. But I contend that if you brought Madame Curie and walked her through a lab today, she would still understand our workflow. She would still see the pipetting, the mixing, the polishing, the samples, the washing of glassware. And so really, why are we still doing this? But that's starting to change. So this is the cover of our Matter article, where we're trying to conceptualize the robots doing manual and cognitive labor. And so our future outlook is over the next couple of decades, we hope to have an exponential increase in the rate of research, how much progress we make. And as we make research cheaper and more accessible by things like the Molecule Maker Lab Institute, right? And the educational area system, we expect more people to be able to participate in research. So if it's cheaper to do research or if it's easier to do it online, not only can those of us in the big, expensive, fancy labs do research, but people in high schools or in community colleges or hobbyists can actually contribute to the body of work, which is exciting for me as well. So I've got some great discussions with Yolanda Gill, professor at USC, who's part of the Nobel Turing Initiative to go after this Nobel Turing Challenge, is really thinking about, where AI is going to be. AI reproduces work that's published or acts as a research assistant or maybe eventually a co-author and is an investigator. So these are the kinds of progressions that we're thinking about. And then just to start to wind down, again, for our workforce, we need to figure out ways to be more inclusive. So this quote here is, children lose confidence in their potential to be scientists, but not in their capacity to do science. And this is especially true for our most at-risk populations. So girls, minorities, and children from lower socioeconomic backgrounds. And so I think as we think about how to make research more accessible, we need to make sure that we're being as cognizant and purposeful as we can about diversity, equity, and inclusion. And so with Marty, we're looking at this billion scientist movement, right? Where as we have this exponential reduction in the cost of research. So in the lower right here, we see Moore's law of research that I'm trying to popularize, where speed goes exponentially up, cost goes exponentially down, right? Just as the cost of transistors went exponentially down, cost of research goes exponentially down. And so just as 3D printers, for example, is revolutionizing manufacturing so that, you can go and print your own part for a fraction of the cost that would take to get it either fabricated or mass produced, of course, we can all do manufacturing. Now, in the same way, we can all start to do research. And so that we hope will cause a rise in citizen science. And so just to try and think of this, what if we were a society of 1 billion scientists? What could we do? What kinds of things could we imagine trying to do? And I think that's really motivating for me, and I know for Marty, to try and get that going. And I think the Molecule Maker Lab Institute is a great way to do that. So with that, I'd like to acknowledge again my collaborators and funding from Air Force Office of Scientific Research at NRC, and I'd be happy to answer any questions.
Thank you for your presentation. And now we can go into the Q&A. There are any questions in the in-person audience? Oh, okay. Yeah. Oh.
Benji, what do you think is the lowest hanging fruit for problems that are actually currently unsolved, but might be particularly amenable to this closed loop engine? And I guess a related question is, you started a slide with maybe the first step is to get AI robots to repeat known experiments. There's a predication in that first step that that's the best way to do science. Does the kind of AI closed loop thing perhaps suggest maybe we should take a step back and rethink how we ask questions and how we answer them so that we can best leverage these tools as opposed to just trying to get them to repeat what we've already been doing?
Yeah, I agree. So I think you were talking about the slide that I showed that came from Professor Gill. And sure, in a progression, I think we talked about that as just, being able to take literature values and show that that's really true. But I agree that that's maybe not the best way to do it, especially because, if you come up with a negative result, you still have to ask, did I do it wrong, or is the paper wrong? And, since you can't usually go back and ask the authors, it's kind of hard to do. But I agree that I think, it's important to try and understand the literature and have that as a starting point. But I think it's more important to move forward and use this resource that we're developing to really attack new and harder problems. And so, the first part of your question was like kind of the low-hanging fruit. And I think, there are really good questions about energy. So organic photovoltaics, I think there's a lot of good work going on in that. I think that's a great way to get going. I think, CO2 capture, sequestration, or of course, the work that we're doing in carbon nanotubes, for me, I think is very much low hanging fruit. But it could also be things like quantum, and as well as, drug discovery work that's going on. So to me, it's a brave new world. I think it's exciting, and I guess to one of the points that I try and make is not only can we go after the big science, but we can go after, as science becomes cheaper to do, we can go after smaller science that's maybe very important to a small number of people. So rare, rare disease treatments, these kinds of things. Did that answer your question, Marty?
Yes.
Great, thanks.
Yeah, I actually have a quick question about your vision about 1 billion scientists. So I'm thinking that if we are really successful, right, in the institute, so we can create actually like 1 billion like a robot scientist very easily, right? So I don't know whether we really need so many scientists to do research. Instead, we can create the artificial intelligence driven robots, right? They can do all the things for us.
So yeah, I agree that we can create lots more robots and we can be more productive. I guess my experience as a researcher is I've always got a lot more questions and good problems to work on than I can ever work on, or I can ever get funding to do, for example. And so my hope is just like, we never complain about having too much computing power, that, as we have research as a resource that grows exponentially, I don't think that we'll run out of questions that we want to research. And as usual, right, more, even as we make progress, more answers leads to even more research and more questions that we want to answer. So that's kind of my expectation of how it will go. I think that it's not so much that we need more researchers. I think it's that the driving force of human curiosity will be essentially infinite and will still outpace our ability to do research, even with lots of research robots.
Yeah, I just saw that. So there's a question in the chat from Michael. The question is, what technologies still need significant improvement or out-of-the-box innovation to make the closed loop more feasible? For example, replacing the peptide with microfluidics. Do you have any opinions on which of these technologies have a lot of promises?
Yeah, that's a great question. Hardware is definitely a barrier right now. So absolutely, we're doing a microfluidics robot now, as are others. And I think automation, not just in the synthesis, but in the characterization, as well as the joining of the two, right? And so thinking about how we make labs and processes that right now are designed for humans and have them be compatible with robots. So sample exchange being a big one. And for chemistry, actually, it's I think wet chemistry is in better shape than, say, materials. Having to take samples and move them from one place to another requires a lot of robotics, and especially if you're going to have a lab that is safe for humans and robots to work at, to coexist. That's another level of design and integration that I think we're just starting to think about. So there are really significant barriers and therefore significant investments that need to be made to just overcome that that problem right there.
Okay, we have another question from Mark. Mark, please unmute yourself.
Yeah, thanks very much, Benji, for the talk. It's Mark Cosdras. I'm from Natural Resources Canada. I'll make one observation. One of the things that we're finding now is that electrochemistry and electrochemical systems are a very convenient way to get in and do things, whether it's electrocatalysts, whether it's corrosion, whether it's plating. All of those things in terms of materials development are working, I think, better and better for us. And I've been dabbling in just about every space that there is. But my question is going to go back to the scientist. The research robots, they don't commercialize devices. Research robots find solutions, potential solutions to device and material problems. Do you think, well, I think that there will be scientists involved in that. They need to be there integrated with these systems. There has to be a subject matter expert behind every one of these. And so would you agree? And then secondly, will the scientists be more critical in commercializing, in translating and transferring the technology in the future because they have more time to do it? Benji, what do you think about those kinds of things?
Yeah, thanks, Mark. Those are great questions and comments. So first, yes, electrochemistry. I think that's a great area. I think I've heard of, seen some work and heard of a lot more work that's really going well in that area. So I think that is an example of Marty's low-hanging fruit. And so on the research to transition side, yes, I think, some people think of the research as the tip of the iceberg, if you will, and that commercialization is sort of a much larger investment. And I think that's true. And I think eventually we'll have to get to the point where, we can apply some of these methods to that valley of death transition point, which I think will be really important. And so that's sort of the next step is, yeah, you can apply autonomous research or autonomous methods to research, and then how do you get it into manufacturing or prototyping? And essentially it's all about risk reduction, right? How can we reduce the labor or the resources needed to reduce risk to get to transition so that we can make something commercial and ultimately helpful to society. And so as far as your comment and question about the role of a human, absolutely. I mean, so when I talk to people doing autonomy, sort of like, and when I first talked about this, it was all about getting the human out of the loop. And so that was wrong. It's really about producing good teams of human researchers and robot researchers. And the autonomy community has absolutely thought about this and worked it out quite a bit. And I didn't show slides on it, which I can show later, but they think about, partnerships and division of labor and trust, two-way trust, right? The humans trusting the robots and the robots also trusting the humans. When your car, starts to take control of you because you've fallen asleep, that's where the robots had stopped trusting you. And so there are examples of that. But as far as, the human being freed then from doing countless experiments and pipetting samples. And by the way, we're losing our STEM students, our very smart students, because they're like, I don't want to do this. I don't want to spend, 3 years in graduate school doing the grunt work because because that's what you got to do to get your PhD. They're like, yeah, I'm going to go to Facebook or, SpaceX or someplace where I can make lots of money and not have to put up with this. And so I think if we then build the research robots that value the graduate students, right, people who have their bachelor's degree and have shown that they can do work already, to do the work, the intellectual work, right, the cognitive work of creativity, insight, supervision, all of those things that robots are a long ways from getting at, then that's what the humans should be doing. And then that becomes a really good partnership where we value the people for their intellectual capital. And as a result, the team of the human and the robot researcher is far more productive and far more powerful than the robot would be by themselves or the humans are right now by themselves. So thank you.
I have one quick follow on if I can, for the moderator. The creative work, absolutely. That's exactly what they need to be there for. One of the things that these robotic platforms will do and are doing is teaching you the process. There still is somebody that has to sit there and say, is it scalable? Is it, can we actually control it in the sense that's not microfluidics and things like that? And what kind of role is it in understanding more of the process? And there's a lot of that discussion through the day today about the process and making sure that's there, but the scalability, and that scientist has a role. What are your thoughts on that? Yeah,
absolutely. I think, there's the contextualization that a robot can't do, right? And it's thinking, I use this chemical, but I can't get that chemical at scale, so that's not a scalable process, right? Or the process is not scalable, or for whatever reason, the robots just don't have access to the contextual information that human researchers have by experience. And so those kinds of things are absolutely important going forward. And so I think, there's no situation that I imagine where the robots are just off by themselves doing research and, writing papers for themselves that they read it, right? It's absolutely humans and robot researchers working as teams, trying to make science go faster and better, and frankly, be fairer in how, what kinds of things we do.
Fantastic. Thanks so much, Benji.
Thanks, Mark.
One more question from the audience. Ocean.
Thanks for a great talk. And in your presentation that you mentioned ideally in 2050, the AI might win a Nobel Prize. So I have one open question: that which field do you think the AI can win the Nobel Prize?
Yeah, I don't know. That's a good question. I think there are lots of opportunities. I would say, I think that the way that I'm really attracted to is emphasizing what I was talking about earlier about knowledge-driven decision-making over data-driven decision-making. So if we just expect, sort of say, okay, computer, here's like lots of experiments, go figure it out and give me back an answer, that's great. It might give you an answer. It might give you a new drug or, a new chemical or new efficient process. But that's not necessarily transferable. And so I think a Nobel Prize will be something that's knowledge-driven, that discovers new science, new fundamental understanding that's translatable, right? That's new laws of physics or chemical reactions that are human interpretable and exploitable, so that we can do things with it. And so that's really what I see happening. And so I maybe not answering your question on purposefully, because I don't know whether it's going to be in medicine or chemistry or quantum. I think it could be in any of those, but I do think it's really going to be knowledge driven rather than data driven. Great. Thanks for your attention, everyone.
Thanks, Benji. Thank you everyone for all the lively and innovative discussions. So this will conclude everything for today's session. I will just remind everybody tomorrow lunch will start at 11:30 a.m. and the talks will begin at noon Central Time. Thank you for being here and I hope to see everybody tomorrow.